Thank you very much for the introduction. Some of you might wonder how a talk with this title ended up in the rewriting session. This will maybe come clear in a few slides. So this talk is concerned with probabilistic model checking and verification, the other big area that has to do with logics in computer science. And the main problem one is concerned here, one wants to model some non-deterministic stochastic processes or systems on which we then want to verify temporal and stochastic properties. Since this can be better explained with an example, I do this also here. So the example scenario we're looking at here is a process migration on a multi-server system. So we're moving processes between servers, and we can describe such a system as a stochastic process. And now there are properties you might want to check, like reachability properties, such as can we avoid certain situations, for example, a situation where servers overloaded, or what is the probability that such a situation is reached within a certain time interval. We might also want to verify quantitative properties, like how often are critical situations entered, or what is the energy consumption of the system. And since these systems description contain both non-determinism and probabilistic elements, what we're computing here can be a range, can take a range of forms. It can be in the form of ranges, averages, or quantiles of the energy consumption, and so on. In modern model checking systems such as PRISM, the way you specify such a system is actually using a program in a programming language. And at the center of this programming language are so-called guarded commands, which we write in this syntax here. So the general idea is you have a guard precondition that is checked against the current state of the system. And when the precondition is met, then the command can be executed, and can be executed with the probabilistic outcome, which is specified again in terms of variable assignments. And what we obtain this way is a state graph describing the different states of the system, where each state corresponds to a variable assignment. So we have here a non-deterministic choice of going into two different states. And from here on it continues, and we obtain a Markov decision process. And on this model, we are now evaluating our stochastic properties that we're interested in. Now, what we were interested in this work is how to integrate knowledge that is formalized in an ontology into such a program. For example, in the server context that we're given here, it could be that we have an ontology describing hardware configurations and constraints that give us further information on how processes should be migrated and can be migrated. So from this perspective, we would like to see the Markov decision process as having states that are description logic knowledge bases, and we assume an additional ontology that gives us some static background knowledge. To be able to model such a thing, we introduce ontologized programs, and these consist of three components. The first component is a program seen in the way we've seen it before, using the programming language of the model checking tool PRISM. We use an ontology that specifies some background knowledge and some static information about the system. And those two components are linked together via an interface. This interface now maps program statements to ontology axioms, and it also uses so-called hooks that allow the program to query the current knowledge base, or the knowledge base representing the current state. So one goal here was to keep the involved formalisms as separate as possible, so that the model checking expert does not have to learn description logics, and vice versa. To illustrate the interplay of these two components, we see ontologized program states like this. We have a command perspective for the program, description logic perspective. We have links between statements that can change over time. And we have a hook, in this case, a hook called migrate server, which migrate server 2, which corresponds to a DL axiom. And we can ask whether this axiom is entailed in order to decide whether we should migrate on the server or not. Now to the question, what does this have to do with rewriting? Our technique to perform model checking on these ontology-mediated programs actually uses some technique which can be called rewriting. Basically what we do, we're given an ontology-mediated program and a property, and we rewrite both into a new program and a new property, which can be checked using a standard tool called Prism. And this has been implemented and evaluated in a previous paper at IFM last year. A question that was left open there is how to handle inconsistencies. Because now our states are knowledge bases, it is possible that an inconsistency is introduced. That is, for instance, we might be running a process on a server where it should not be running. And to handle these cases, we introduced 3 possible semantics, which basically specify how these MDPs look like. One approach is to allow the inconsistency and let the program handle it. Another way would be to remove inconsistent states and normalize probabilities accordingly, so that we wouldn't move a process on a server where it shouldn't be. And a third option, if the probabilities are considered fixed and should not be normalized, we have the probability preserving semantics. So we looked at these 3 types of semantics and considered the problem of determining whether this program is consistent with respect to the semantics, and analyzed the complexity for a general class of DLs. What is still open so far is how to actually perform model checking and whether our rewriting approach can be adapted. It currently looks like we're more heading towards an adaptation of the model checking tool to be able to perform model checking tasks with inconsistencies. And with that, I conclude my talk. I think I should also be at the end of my time. Thank you very much.